Hello, this is Concrete Path. Today we'll be solving one question by using different methods of deflection of beams. So let's go and get that problem. So there are two concentrated loads acting at C and C dash. You have to get the relative moment of AA dash, relative moment of AA dash, and CC dash, and assume that this member BB dash is actually rigid. So let's go start the problem. And EI is constant for all the members. So let's start by solving this question by firstly let's take by superposition method. Number one, superposition method. So for that we had to get the free body diagram of the entire structure. Let's take that structure into parts. Let's say this is the structure. यहाँ पे आपका लोड P एक्ट कर रहा है, तो इसको बैलेंस करने के लिए यहाँ पे इंटरनल फोर्स P डेवलप होगा एंड एंटी क्लॉकवाइज मोमेंट and clockwise moment of P into L, that's P into L, and यहाँ पे load P, and same will be transferred. Actually that member AB, in that member AB में कोई load भी नहीं आ रहा है, तो अगर यहाँ पे आप load transfer करोगे तो ये this won't be in equilibrium because there is इस load को या इस moment को balance करने के लिए कोई एक्सटर्नल और एक लोड है ही नहीं इसको बैलेंस करने के लिए. That means it would not take any internal force from the member CB, so it would remain without loads. The all load will be transferred to the member BB dash. So we will be transferring this force into this one here P, and यहाँ पे आपका clockwise एक्ट कर रहा है तो यहाँ पे एंटी क्लॉकवाइज BL. सिमिलरली यहाँ पे लोड P एक्ट कर रहा है तो यहाँ पे P, so इसको बैलेंस करने के लिए एंटी क्लॉकवाइज P into L, and then same would be transferred to this part and actual force P. So this would remain without any load. This would remain without any load. Then we can also show that that joint B also. Say यहाँ पे आपका P would be in this direction. After यहाँ पे आपका P was in the negative x-axis, so we'd write in bit after that the joint, this joint B dash, that joint B, तो इसमें loads would be in the opposite direction, so this is B, and आपका यहाँ पे clockwise moment था तो यहाँ पे हम anti clockwise PL दिखाएंगे, and यहाँ से हम zero करेंगे, show that यहाँ पे कोई load नहीं transfer होगा. Then that load would be transferred to this member that's called as BB dash, so we can write this is P and this is anti clockwise B into L. So same would be then transferred to the actual BB dash. This was at the joint B. Now if you see that on the member BB dash there is some hogging bending moment developed. So because of that it looks like a simply support beam, so it would deflect upwards. So deflection profile would be somewhat in this fashion. Yeah. Now you have to maintain that structural configuration that initially आपका member, this was your member BB dash and member AB dash was like this. So यहाँ पे 90 degree maintain करना है आपको. This was A, this was B, and C. Similarly, if the member BB dash has been deflected by this because of this curvature, so you have to maintain the slope also that 90 degree. But one thing is that in the member BA there is no load, so that it will remain as a straight line. We know that the curvature relation 1/r equals to m by EI. If the bending moment is 0 in the member, that this curvature is 0, that means it will remain this as a straight line. So it would remain as a straight line. Now उसके बाद देखते हैं हम कि the member BC dash is member BC is also that this was BB dash. We can see that member BC, this was also maintaining 90 degree initially. तो आपको 90 degree maintain करना है. It should maintain 90 degree. Let's say it should have maintained that 90 degree. See, the profile should have been this way, but because load is acting in the part BC इस BC में भी एक्ट लोड कर रहा है, तो उसका इफेक्ट भी हमको लेना होगा. We can treat it as an imaginary beam because moment भी यहाँ पे है और shear force भी है. We can treat it as an imaginary beam. Then the load is acting at the end span. We can say it will deflect in this fashion by some amount of alpha. So it will deflect by some amount. We can show that also. Let's say that the deflection here would be somewhat in this fashion. Similarly in this fashion also, in this part also. So finally we can say, let's say this, we can say that this is theta. So this would be also theta. This is theta, this is also theta. And this is also theta. Can you say that this is theta? Can you say that? Can you say that this is theta? If this is theta, this is theta, and this is theta. This is 90 minus theta, you can show. 90 minus theta. This is theta. So we can say that it has deflected. Let's say the length is we will be providing that the length was, say this length was L, this was also L, this was length L, this was length A, and this was length A. So we can say how much that point A has shifted outwards. We can say this has shifted by an amount of A into theta. A into theta. Similarly, this part also shifted by an amount of A into theta. So finally, we can say how much deflection, how much movement of A dash is there, relative movement. We can say that's equals to 2A theta. Relative movement of A dash is equals to 2A theta. Now you need to get the value of theta. So for the theta, you need to say, think it as a simply support beam with two concentrated moments at the ends. So we know that deflection value at this part would equals to ml by 2ei. So we can write that's 2 into A into theta. Theta we can write as the value of theta is ml by 2ei. But what is the value of m? M equals to P into L. So m equals to P into L. M equals to P into L. We can write ml by 2ei. So final relative displacement of A and A dash is equals to PL square A by 2ei. So one part of the question is over. Now we are left with how much. So if the point A and A dash is moving outwards. Now to maintain that rigid connection at the point B, at the joint B, at the joint B, आपको यहाँ पे आपको maintain करना है 90 degree between the three members. So because of that effect, your C and C dash is going inside. That are closing the gap. So we can say C dash are closing the gap. We have to say how much closure is there. So we can say this part it is equals to L theta. This is also L theta, and this is, we assume that this is alpha, and this is also alpha. So final C is there, C dash is here. So we can say total relative displacement between the 2 points is equals to 2 times L theta plus 2 that alpha. So we know that 2 times L into theta was equals to ml by 2ei, but the value of m was P into L. Okay, right, P into L ml by 2ei plus alpha. We know that alpha का value क्या है यहाँ पे when we say that treat it as an imaginary beam. This was length L, load is acting at the end span. We can write PL cube by 3ei. So we can write that also, PL cube by 3 EI. So finally your value would come out to be equals to 5 by 3 PL cube by EI. 5 by 3 PL cube by EI. And this was the method. This was to get the deflection by using the superposition method. Now if we say let's use the method of moment area method. If we solve by the moment area method, let's write that moment area method. Moment area method. Now see free body diagram तो आपको बनाना पड़ेगा ही. In every method you have to get the free body diagram of this structure, because loads are acting only at the point C and C dash. You don't know what's happening inside, so for that you have to see what are the forces developed in the all members separately. So the configuration is the same. Now you need to get the value of, by using moment area method you can get the value of that deflection, which I called as alpha. You can get the value of alpha, and you can get the value of theta by using moment area method. Rest of the deflection values are same. Relative moment would be same between A and A dash and C and C dash. बस आपको find करना है कि how you can get value of alpha using moment area method, and how you can get the value of theta using moment area method. So we can get alpha value by using moment area method, theorem 2, and this one by theorem 1. Theorem 2 and theorem 1. So let's say how you can get the value of theta. How you can get the value of theta. Say if you have simply support beam with a that concentrated moment acting at the ends, so you can say your BMD would look like this one. Can you say shear force diagram is 0? Because यहाँ से आपका M आ रहा है, यहाँ से भी M आ रहा है, तो इसका इफेक्ट इसको ये वाला कैंसिल करेगा. Shear force would have been M by L, because this is M by L, say at any support this is M by L, next one would be minus M by L, so they will cancel out each other, and there is no external loading also, so you can say shear force is 0, so your BMD would look like M, and you divide by EI, that's your M by EI between the 2 points length of L. So we need to get the value of that theta. So we need to get the value of theta. So we can say theta at any point B, that equals to from the theorem 1. If I use theorem 1, I would say I know that point at the midspan loading is symmetric. Theta is maximum at the theta is 0 at the midspan. So if I draw a tangent at the midspan, or I can say if I draw a tangent from the support B, and if I say that here the theta is 0, I know theta is 0 here, then I say this value I can call it as theta at mid with respect to the tangent drawn from B, that is equals to area between the 2 points in the M by EI diagram. Area BM, we can say. So this area BM, I can say this is the theta. This is area of this one will give me theta. So we can write theta MB equals to theta M minus theta B, that equals to minus M by EI into length of L by 2. What is the value of M? M equals to P into L. So we can write minus P into L, but that's PL square by 2 EI. So we get the value of theta MB, but theta M is actually 0, so we can write minus theta B equals to minus PL square by 2 EI. So we got the theta B. Finally we can write in this part also that we can write in this part theta B PL square by, we can take the magnitude also. We can say if it would have been negative, if the theta B would have been negative, we can say let's take the magnitude only, because if you want to say because of some theta, what is the deflection at this length, at this point, we can say this is some length L into theta. So we can say this is L into theta. It won't say it is minus L into theta, so we can say it's L theta. So let's take the magnitude also, PL square by 2 EI. So we got the theta. If you substitute here PL square by 2 EI, so we would have written that 2 into A PL square by 2 EI. that's similar to what we got the result, that PL square by AEI. PL square by AEI. Actually, it was PL square by A, PL square A by EI. PL square A by EI. So we got the value of theta, that's PL square A by EI, PL square by 2EI. So for this member, we can say L theta equals to L into PL square by 2EI. That's also same here. So now we need to get the value of deflection, between the 2 points. So we know that if I draw tangent from A, this is tangent from A, I can say this is tangent drawn from A, and I can say this value of delta, this delta I can call as delta at C with respect to tangent drawn from A. That's equals to centroidal distance of the area between the 2 points about the point C into area. So we can say XC into area. So what is the area between the 2 points in the M by EI diagram? Can we draw the M by EI diagram of this part? Can we draw? See, in the part AB there is no load, but in the part BC there is some moment developed. So we can say this was somewhat in this fashion. If I write that B is acting here, then there is no load. Let's say this is a theta. Let's say this is fixed. This is fixed, and actually there is no load in this part, and we can treat it that यहाँ पे आपका moment maximum आ रहा था. At this point there was some maximum moment, so we can say let's keep it in this fashion. Up to this point, यहाँ पे आपका maximum moment was developed, that is equals to, because of this effect, it would create anti-clockwise moment. That's negative moment. If you are seeing from this side, you have to see inside the frame. So a negative anti-clockwise moment is developed. So we can say this is negative BMD would be developed there. That's equals to P into L minus PL by EI minus PL by EI. Then after that, it would remain straight line in this fashion. So the centroid is here. From the point C, we can say this is the centroidal distance of 2/3 of L. So we can write that's area of that we can write alpha equals to 1/2 PL by EI negative 1/2 PL by EI into length L into 2L by 3. That's PL cube by 3 EI. We can keep the magnitude PL cube by 3 EI. That's also same here, PL cube by 3 EI. So finally you can get the same value of 5/3 PL cube by EI. Now let's solve this one again by Castigliano's method. Castigliano's theorem. Castigliano's theorem. So for that, you had to for the relative moment of A dash, there was no load acting. So you have to show that also that if you want to say let's solve by Castigliano's theorem. So यहाँ पे the structure was somewhat in this fashion. So you have to apply also a pseudo load acting at this point. Let's say that's called as a load of H here. This is pseudo load. H is pseudo load because it was not acting in the actual question, that problem. Pseudo load. Then that equals to 0. And the loads that were present already, we can say that were at the support at the point C and C dash. C and C dash. This is point B and B dash. This is A and A dash. So you have to make the free body diagrams of these. We can show them separately. Let's take that. Let's say this is H. तो यहाँ पे आपका H होगा and anti-clockwise moment of H into A. Similarly in this part also, this was acting in this part, in this way, we can write h into a. Yeah, it's the direction is here. You have to show it in this way. We know that a dash are moving away, so you have to apply. Let's assume you are applying a pseudo load in the same direction so that they would go away from each other. So you are applying h in this way, and here the reaction developed would be also h, and a moment of clockwise h into a. Similarly, यहाँ पे आप h अप्लाई कर रहे हो तो यहाँ पे h होगा and anti-clockwise h into a. So similarly, यहाँ पे आपका member BC है, BB dash. Then after that, you have to transfer this effect also, that this load is acting here P, so internal force P and clockwise P into L. Similarly, in this one, load is in this way, reaction is in this way, and P into L in this way. Now, see, इसका effect it is in the clockwise, so इसका moment जो transfer होगा, that would be anti-clockwise P, that equals to H into A. And similarly, this one is also clockwise, so इसका effect be that would be transferred anti-clockwise. We can write HA plus R PL. Similarly, this one is your H in this direction, positive axis. So, and this one we can say this is in the negative x-axis. So we can say let's take the sign of P, fine, net value of P. We can say in this part there would be P in this direction, but H is in this direction. So we can say let's keep the sign of the P value. We can say net value of P minus H is in this direction. Similarly, here we can say from by the symmetry we can say this is this fashion. This the moments free body diagram, bending forces and moments would be in this way. Is it clear? Are you okay? And now you have to say there's some bending moment at the ends, so there would be a theta developed in the part B dash. So similar fashion में हम कहेंगे, let's say this is theta, theta. So to maintain that, now in the member that AB dash also there is some deflection now. There would be some deflection because of that ice load. So we don't worry about that now. We would use directly that Castigliano's theorem. We know that Castigliano's theorem says that delta at any point A dash relative, that's equals to strain energy stored, that m square dx by 2ei. Also we can say m small m dx by ei. Let's if I use directly that moment at any x, see, if I cut at any x in every segment or in every member, if I cut section at any x, there is only one single load acting. So whether your moment equation becomes minus px or plus px, because it doesn't affect here, because your moment, if I keep in terms of strain energy, that's a function of m square. So आपका अगर minus m px होगा या hx होगा minus hx होगा, आपको उसमें square डालना है, तो it won't make any effect as long as there's only one load acting. Okay, let's say how much strain energy is developed in the structure. Would say strain energy, let's say in this part, this is one member and one member, so same we can say 2 into strain energy stored for in the member, that's the moment developed here is h into x whole square dx by 2ei, and the range is from 0 to a. Similarly, we can write plus twice that is here the moment developed is p into x minus px hoga, it doesn't matter here because one load is acting, so we can write px whole square dx by 2ei. And third one we can write in this member bv dash, there's, if we cut at any x, there is a bending moment that's constant, bending moment, that's ha plus pl into pl square dx by 2ei, ranges from 0 to L, and this is only one member, so you have to integrate it. you need to get the value of strain energy. So this is the total strain energy, and we know that delta at any location a dash relative delta displacement between any 2 points, that's dou u by dou, and the with respect to the load you are applied at that location. Since we applied load at a and a dash both points, so we get a relative displacement between the 2 points. So let's solve that. We would say, now if you integrate it, we can say dou by dou h. You have to integrate it with respect to h, and also set, then you have to set h also 0 after that. So if you integrated this part, it would become 2 into actually it was initially, you can say it was h square x square dx by 2ei. Now you are differentiating it, and also integrate, you have to integrate and also differentiate with respect to h. Sorry, let's solve first one step. Let's solve for one step, then we can go. Let's solve for one step. Let's say that this is h square x square dx by 2ei, and this is 0 to a plus 2 times 0 to l, p square x square dx by 2ei, and third one is your 0 to l h into ha, that's s square a square plus p square l square plus 2 times ha pl yeah, dx by 2ei. Now if you integrate it, if you differentiate it now with respect to h, let's say you are now in this was your total strain energy. Now you say dou u by dou h, that equals to, we can write 2 times 2h x square by 2ei, and you have to integrate also that, then you have to integrate also 0 to l 0 to a dx, plus similarly you can write for this fashion, for this one also, that p square, and we can say that differentiation of this part would be 0 with respect to h, so this one becomes 0, then plus in this part will go 0, the remaining would be this one, we can write 2h a square dx by 2ei, then integrate it with respect to 0 to l plus, and this part we can say differentiation of this one, that would be 2apl dx by 2ei, integrate it. So if we solve that, what's the value of this particular thing that's coming out to be equals to, let's say now you have to set h also 0, set h to 0, so this part also goes, and this is also h, function of h, so this will also go, and the rest part that's remaining, that's this one, we can write this is apl dx by ei, integral 0 to l, that equals to pl square by 2 pl square by ei, I get pl square by ei into a. Do we got this value? But the theta should have been pl square a by 2 ei. Yeah, it's deflection. It's deflection related to displacement of the a dash, delta a dash. Do we got this value earlier? A dash, delta a dash. Yeah, we got this values, same value of pl square a by ei. Yeah. Now to get the value of deflection related to displacement of point cc dash, we can say there is no need actually of this this pseudo load h acting at that point. Now if you want to say what is the strain energy is stored same, no, we can say, if I keep the strain energy stored as that of earlier, that delta a for calculation. So if I say strain energy was same, only you have to say h value equals to 0. H value equals to 0. If I set h value equals to 0 earlier, before solving for delta, if I say h value is 0, if I have to calculate the effect at cc dash, I can say this is 0, and this one is remaining, and effect of this HA is also 0. So we have to solve only this part now. Understand that? Understand that? Let's solve total strain energy. So this is our strain energy. See, remember B dash was assumed that it was given that it is actually rigid. Otherwise, you would have to take that effect of that P load acting on the member BB dash. So we would have write P square dx by 2AE. P square dx by 2AE. Let's say now, let's say you want to get delta cc dash relative. So we would say dou u by dou. Since there is already applied load acting at that point cc dash, so there is no load need to apply a pseudo load at point C. So we can say dou u by dou p, that's already acting there at that point. At the both points C, that load P is acting. So we can say this will give me a related displacement between point C dash. So if I differentiate this strain energy, total strain energy, we can write this is 2 times integral 0 to L. Then I write dou by dou P of P square x square dx by 2EI. Similarly, plus 0 to L in the part B dash, this one. So we can write P square L square dx by 2EI, and you differentiate it dou by dou P. So we can get some value. Let's write that this is P2P. Then we write x cube. We can write x cube by 3 anyway. So we can write x square dx in this fashion. Zero to L. That's P. That's L square. Then it's remaining 0 to L dx by 2EI. 0 to L. You can write in this fashion also. PL square by 2EI. Yeah. So your value here is, it comes out to be equals to P by EI and L cube by 3 plus PL cube by 2EI. Is it 2 here? Yeah, it should not be 2, because when you differentiate it, there should be some that this 2 power would go down. So finally it would remain as PL cube by EI. So finally you are left with 2 by 3 plus 1, that's 5 by 3 PL cube by EI. So delta CC dash. That was also the same value which we got earlier. Here we can see 5 by 3 PL cube by EI. By 3 PL cube by EI. So let's have one more problem by using 2 different methods. Would say we'll take one problem that's called as a simply support beam of length 6 meter, loaded symmetrically. We have loading symmetric, but for that middle part of that, you can say 4 meter inside, 4 kilonewton per meter. That here the loading, if we have fixed hindered support, roller support, you need to get delta maximum. Can you say why is the delta maximum? Why do you think delta maximum would be there when the loading is symmetric? So I think delta maximum is at the mid. See, we can solve this problem by different approaches. Let's think of that. First, calculate that reactions. If I say, what's the reaction here? I would say total load is 4 into 4, that's 16. So you divide by 2, that's 8 and 8. Now, if I say, what's the bending moment diagram? If I think that this is the bending moment diagram, 8 ones are 8. Then after that, you have a uniformly uniformly distributed load. Because of that, the effect of BMD would be a 2-degree curve. So maximum would be at the mid. So this is some 2-degree curve up to this point. And after that, it is a straight line. This is 1 degree, this is 2 degree, and this is 2 degree, this is 1 degree. So is calculation of M by EI diagram easy if you use moment area method or conjugate beam method? Is it easy? This part is easy, but what about this part? To get the centroids of these, then it's very difficult to solve by moment area method or conjugate beam method. So we are left with Macaulay's method. We are left with, we can also solve by Castigliano's theorem also, but let's say we are using Macaulay's, and we can say, let's think of superposition also. Superposition. So calculation by moment area method and conjugate beam method, it would be difficult. You can solve this by these two methods. If you replace it by some, that if you solve by BMD by parts, I have told you how you solve BMD by parts. You can take any point that's and assume that that's a fixed support. Let's say support B is fixed, then you apply load here, then you see what's the effect of these, then you calculate overall effect. So we'll be solving this method by Macaulay's method. Let's solve by Macaulay's method. Now, firstly, let's solve by Macaulay's method. Number 1, Macaulay's method. So it says that get the moment equation for the entire structure just dx before support and support. Let's say you cut a section at x just before this just before the support and support. So this is x. We can say, let's get the moment equation. We can write 8 into x plus, and we can treat it as we have to modify the UDL because it's Macaulay's. It says that modify the UDL till the point x is reached. Modified UDL and UVL. So you have to modify it up to that point x, and similarly in this fashion also. You have to show it up to the point that end support also. So we can say that's 8x plus 4x minus 1 meter, then x1, then square by 2 minus, and this was minus because it's anti-clockwise, so we're at minus, and because of this effect is small one, then we can write plus 4, and it is acting after 1 plus 4, 5 meter, so we can write 4 into x minus 5 whole square by 2. And then we say that here the moment is some moment mx, that's anti-clockwise. Then finally we can write it is a clockwise after transferring though. So we get the equation of moment at any x. So let's apply those oblique signs. Now we can write that equals to ei d2y by dx2. Now if I say ai into theta, that's equals to 8x squared by 2 plus constant c1. After that I can write minus 2 x minus 1 cubed by 3 plus, I can write 2 into x minus 5 whole cubed by 3. So after that I can once more integrate it and get ei delta. That's 4x cubed by 3 plus c1x plus c2. That's minus 2 x minus 1 power 4 by 12 plus 2 by 12 x minus 5 power 4. Yeah. Now I would say, do I know the deflection values at x equals to 0, delta is 0? I can write boundary conditions boundary conditions that at x equals to 0, delta is 0. That means from this equation you can get C2 equals to 0. Similarly, at x equals to total length of at x equals to length of L, total length of this beam is equals to 1 plus 4 plus 1, that's 6 meter. So if I write x equals to 6 meter, delta is 0. So we can write 0 equals to 4 6 cubed by 3 plus C1 into 6 minus 1 by 6 of 6 minus 1 power 4 plus 1 by 6 of 6 minus 5 power 4. So you get the value of C1, that's minus times 92 by 3. So you got the value of C2, C1. Now we know that delta would be maximum at the mid. Delta is maximum at mid. Delta is maximum at the mid. So if you substitute the value of x equals to mid, that's 3 meter. 3 meter, you can get the value of, we can write EI delta maximum, that equals to 4 into 3 cubed by 3 plus minus 92 by 3 into 3. Then we write minus 2 by 6, 2 by 12 into 3 minus 1 power 4. Then after that next term we can write 1 by 6 of 3 minus 5 power 4. Since this value it's negative, so we have to ignore it. Ignored. So this part is ignored. Now you calculate the value delta maximum. That equals to sometimes divided by EI minus 176 by 3. So we write downwards deflection at the mid. Now this was by double integration, or we can say Macaulay's method, but it was so it took a lot of calculations, but the procedure is very easy. But you had to solve it. Now if I say, can I solve it by superposition method? Let's take off superposition method. By using the concept of imaginary beam, let's say by superposition method. And concept of imaginary beam. We say that let's think of this one. We know that here when we draw the BMD, there was some value of bending moment at the mid. If there is bending moment at the mid, there is some shear force. Let's say shear force is 0, but we can treat it as a fixed support here. Because deflection is also 0, that theta is 0 also there. We can say it's behaving like a fixed support. If I make a fixed support here at the mid span, if I make a fixed support and solve from one of the side, so if I say initially the beam was in this fashion, now you applied a load of that upward load of 4 kilonewton per meter for length of, this was your 2 meter, and a load here, the reaction was 8 upwards, so you are applying a load of 8 downwards. I can assume that 8 kilonewton. So it would have two effects. We can say then we separately solve those by using the concept of superposition. Let's say we are dealing that same way. Let's say this was your fixed support, then and a load of UDL acting for 4 kilonewton per meter acting for 2 meter, and plus you are having a load of 8 kilonewton in the opposite direction. This is downwards, this is upwards. Let's say this is upwards, so it would deflect in this fashion, it would deflect in this fashion. So there is some theta. The theta here are also same, and you got some value of delta 1 here. This is also delta 1, and this one would be 1 into theta. Similarly, this value of deflection would be 8 into 3 cubed by 3i. Total length is 3, so we can write 8 into 3 cubed by 3i. Let's take it as positive upwards, and for this one you can say value of this one, delta 1 would be equals to W L to the power 4 by 8ei plus theta. Theta value is W L cubed by 6ei into length of 1 meter. So you have this value. One value is positive, one value is negative. Let's say any one value is negative or positive, then you would say delta net equals to delta A minus delta B. So you get the value, net value, that's also same, 176 by 3i, 176 by 3i. Let's say it was positive or negative, you can say, but then we can it's not that sign is not important, so you can get the value. So this was all for this lecture. Hope you enjoyed the lecture.